Hello everyone, and welcome to our very brief discussion on the derivatives of inverse trig functions. So let's start with inverse sine, one of the biggies, inverse sine, inverse cosine. And the first thing we can do is remind ourselves that the inverse function, right, is working backwards from the range back to the domain. So if we have y equals sine inverse of x, this really means sine of y equals x, right? The variables change places when we're talking about inverses to regular functions. And we have to remember that we have to restrict the domain of the sine function in order to get an inverse function, right? We have to restrict it to make it 1 to 1. So we're going to restrict that domain of sine to be from minus pi over 2 to pi over 2. So on the unit circle, right, we're restricting it to these two domains, minus pi over 2 to pi over 2. Because this gives us a full cycle of sine, right? It gives us all the negative values, 0, and all the positive values, and it doesn't double up. So that way we can make it a 1-to-1 function when we take its inverse. Okay, so now that we remind ourselves of what the inverse function is, let's differentiate this, right, implicitly with respect to x. Well, we know the derivative of sine is cosine, but because we're taking it with respect to x, it's cosine y, and then the derivative of y with respect to x, which is just dy dx. And then we take the derivative of this with respect to x, and that gets to be 1, right? So we're remind yourselves of what implicit differentiation means, that we're taking the derivative with respect to x. Then if we solve for dy dx, it's just a matter of dividing by cosine y. We get this. Now, we know that cosine y is always greater than or equal to 0 in this interval, right? Because if we go back and look at our unit circle, cosine, remember, is our x value. And in this entire interval, cosine goes from 0 out to 1. So because of that, we can use our Pythagorean identity to solve for y, right? To solve for cosine y. So we subtract the sine squared over here. Then we can take the square root of both sides, and because cosine is always positive, we don't have to worry about the plus and minus of the square root. We just get the square root, right? We get the positive version of it. So that's how we can get this concept here. But because we made this definition up top, right, because we set this, we have this equal, which means the same thing as this. This has already been defined as what x equals. We can do an x substitution, and just this becomes that. So now we can put it all together and realize that dy dx equals 1 over cosine y, which is what we had before, right? We had dy dx equals 1 over cosine y. We just showed that cosine y was the square root of 1 minus x squared. Put it all together, dy dx equals this. And remember, 1 over cosine y was where we got the sine inverse of x when we took its derivative. And this is now the answer, the final answer for the derivative of the inverse sine of x. Now, following a similar, set of steps where if we let y equal tan inverse of x, then that means that tan of y equals x. We do the same implicit differentiation, and we do a bunch of work, right? We get the derivative of tan is secant squared y. We solve for the dy dx like we did before. We do our Pythagorean identity substitution here. And then, because of that, we can sub the x back in for this. And so now we get the answer for tan inverse. The rest of them are proven with similar steps. I'll leave it up to you to go and do those on your own if you want to, but here they all are in one space. So these are the derivatives of all 6 of our trig functions. You'll see that all of them involve fractions, and they involve, x squareds and some other x's and plus and minus ones, and a lot of them have square roots. And it kind of makes sense that they're all similar because remember, the trig functions are all highly related, right? They're all built off of sine and cosine, so it makes sense that their derivatives should be somewhat similar. All right, let's look at a couple examples. Let's see if we can differentiate now 1 over sine inverse of x, and then x times. Arctan of x is just a different way of writing tan inverse of x. So if you see like arc sine or arc cosine, it just means sine inverse. The only reason why we do that is because the typesetting of putting the -1 is difficult in all things. It's easy to put in a book when you have a publisher, but it's not easy to write like in an email. So arctan is a much easier thing to delineate the same thing as an inverse tangent. Okay. Anyhow, let's look at the first one. We can rewrite this as the whole thing to the -1 power and then use the chain rule. Right? So something to the -1 becomes -1 times the thing to the -2 and then times the derivative of the thing, right? The inside bit. Well, this whole thing minus, right? There's the negative, and then to the -2 just means it goes on the bottom of the fraction squared. We already know the derivative of this is 1 over the square root of 1 minus x squared. And there we go. We're done. That's our answer. Now, for the second one, we take the derivative of arctan, or x times arctan, which remember we have to use the product rule now. So it's first times the derivative of the second plus the second times the derivative of the first. Well, luckily, the derivative of the first is just 1, so that's the easy piece. This is the big, ugly stuff that comes from the derivative of arctangent from over here. Now you may notice some weird things going on in here, but you have to remember that we're taking the derivative of arctan of this square root of x. So it's kind of like thinking, okay, if we have, tan inverse of a box, according to our formula over here, we get 1 over 1 plus the box squared. Right? The derivative is just going to be 1 over 1 plus the box squared. Well, now, instead of the box, it's square root of x. So the square root of x goes in here, and that's why we have this. But, again, because this isn't just x, when we take the derivative of arctan of this stuff, we get this pattern, but then we also have times dx, right? The derivative of the x when it's normal. And this is just 1 normally, but because this is no longer x, we now have to have the derivative of the square root of x with respect to x using the chain rule. And that's where this comes from, right? Because the square root of x is x to the 1/2 power. You use the power rule, the 1/2 comes down, and then it goes to negative 1/2 power. Then you're going to combine this and this, right? Because 1/2 x to the negative 1/2 really just equals 1 over 2 root x, right? Because it's x, 1 over x to the 1/2 power. And then you got this x up on top, and x divided by the square root of x just becomes the square root of x on top. So that's where this piece comes from. And then, of course, when you square a square root, you just get x. So that's where that one comes from. So all this weird stuff is really just coming from, well, A, the product rule, but then inside the product rule, we had to do the chain rule. So it's a good little refresher of both of those rules. And that's all I've got for you. Those are the two examples.